I think we can move on to the next presentation then. Thanks again for this nice presentation. I'm sorry we cannot really applaud. We have the virtual environment. Thanks once again.
Thanks.
Okay, so we go to the next talk. It's still a full-length paper. And the paper is on fuel and Markov decision processes, practical approach to consumption. And the presenter is Pranay Thangeda. And again, apologies for possibly wrong pronunciation of your name. So please go ahead. You have 15 minutes for presentation, and then we have about 5 minutes for question time.
All right. You can see my screen, right?
Yes, I can see your screen, and I can also hear you.
All right, that's great. Thank you. Hello, everyone. My name is Pranay Thangeda, and I'm a graduate student at the University of Illinois Urbana-Champaign. Today, I'm going to present a work titled FiMDP, Fuel and Markov Addition Process, a Practical Approach to Consumption. This is a joint work with Francois Blaudeck, Murat Kubukape, Melky Rodnick, and Ufuk-Tupko. So here's a quick overview of the talk. We're going to introduce what kind of problems that are of interest to us and why they're practically important. Then we're going to introduce the notion of consumption Markov addition process. After that, we'll provide an overview of our tool, FiMDP, and discuss some of the features of FiMDP. Then we'll talk about FiMDP, and it's a package with a bunch of interesting environments for FiMDP. After that, we evaluate our tool and compare it with other possible approaches to solve the same problem, and also try to show the scalability of our tool. And finally, we conclude the work and talk about some future directions. So developing control strategies for agents operating in stochastic environments is generally a problem of interest. Let's say you have a rover operating on a Martian surface with unknown dynamics. Usually the dynamics are modeled as stochastic dynamics. And even in the case of, let's say, an autonomous electric vehicle operating in a dense urban environment with stochastic travel times, even in that case, there's inherent stochasticity in the environment. And environment stochastic dynamics are usually modeled as discrete time Markov addition process. And once you have an MDP, traditionally the way to obtain a solution is you obtain a policy which essentially specifies an action of interest at every state. However, apart from the stochastic dynamics in the environment, often the agents have some sort of resource constraints on them. And they're pretty inevitable in most realistic systems. For example, in the case of autonomous ride-sharing vehicles, you have to recharge the electric batteries at some point, and you have to reload the energy back to the state to proceed in your route. A naive approach would be to append the resource level as a part of the state, and then you can enforce some sort of a constraint on the lines of always make sure that the resource state is greater than 0. However, this multiplies the size of the state space by the number of possible resource levels, which in any realistic problem would significantly increase the computation required to get a policy or a solution. An alternative approach that we use in this paper, we model the problem by something we call as the consumption Markov addition process. So the consumption Markov addition process has a finite set of states and also a finite set of actions. And the transition probability function that essentially dictates how the agents behave for a given action in a given state. And these are elements you typically see in a traditional Markov addition process. There's nothing new about that. But apart from that, you also have a consumption function, which dictates, gives some notion of consumption for every state and action pair. And then you have a set of reload states. And these reload states are where the agent reloads its energy. And you also have a cap, which is a capacity. And the agent reloads to this capacity in each of the reload state. The notion of consumption Markov addition process and the associated algorithms were first introduced in the author's previous work in the paper cited here. And we build upon that work and implement the algorithms in our tool. So we introduced the definition of consumption Markov addition process, but once you have a consumption Markov addition process, the agent tracks both the state and the resource level separately. And the agent uses something we call counter strategies to select an action given in a given state at a current resource level. So the action not only depends on the state, but also depends on the resource level. For example, if you're in a state and if you have very low resource, then you'll probably want to end up in a state that leads to a reload state rather than leading to your goal. The counter strategies here the counter in the counter strategies here is not in the sense of a counter example, but more in the sense of a counter which counts the resource level. And the strategy is pretty similar to what we use in an MDP. The decisions are not specified for each resource level, but for intervals of resource levels. And in our previous work, we proved that providing counter strategies with polynomial size representation are sufficient for guaranteeing mission success with probability of 1. And we also proved that these strategies can be synthesized in polynomial time. So far we discussed what the problems of interest are, how do we model them, and why do we model them that way? That's because we were able to obtain valid controllers in polynomial time. Now let's talk about FiMDP. So FiMDP is a tool that enables us to design and analyze consumption Markov decision process, and also enables us to synthesize resource-aware control strategies for consumption Markov decision process. It's a tool written in Python 3. There are no dependencies for FiMDP, at least for the core functionality. We do have some dependencies for some extended functionality, and the three major dependencies are Spot. We use Spot for translating LTL specifications into deterministic Beek automata, and we also use Storm for translating some of the models in standard languages into our model, and we use GraphViz for visualizing some elements of the CMDP in an interactive fashion. The tool is published in Python, the Python index, and installing it is as simple as typing pip install FiMDP. The main goals of FiMDP are practicality and education. We want people to be able to use the tool actively, and that's the main motivation behind enabling interface with standard languages, standard modeling languages, including Prism. And we also want users to enter a wide range of specifications, and that's the reason why we enable the functionality with the LTL objectives. In terms of education, the tool is pretty easy to get started with, even if you lack the technical background. We provide a lot of tutorials in Jupyter notebooks that essentially gets you started with the tool pretty quickly. Yeah, and the code is obviously open source and well documented. You can find the code, a code base in this organization, and the documentation at this location. All right, so there's no fun in talking about a tool paper without actually using the tools. So let's do that. So this is standard syntax for creating a consumption Markov decision process in FiMDP. So you have the standard boilerplate, you import the tool and then set up the environment to be able to visualize things. Then you first create an object of the class, the consumption MDP. After that, you declare the number of states. And if you want to, you can assign labels to each of the state. Then you have to assign states to assign reload state, some of the states as reload states. In this case, we assign states with the index 0 and 4 as the reload states. After that, we add actions where we have to mention the source node, distribution, and some label for the action and the consumption for each of the action. And we add a bunch of more actions. So if you notice, we have an action alpha for every state, which is deterministic, and we have an action beta only for state 1, which is stochastic. So this is a quick visualization of the consumption Markov decision process, which we just created. Each node is a state, and the node with 2 rings are reload states. So we have deterministic action everywhere except the node S, and we only have single action everywhere except node S. Node S has one action beta, which is stochastic, and the consumptions are recorded right next to the actions. So once you have this consumption Markov decision process, before synthesizing the strategy, we want to be able to talk about what kind of strategy we're synthesizing. So what exactly our objective is. So given a set of target states or accepting states, FiMDP offers a bunch of different objectives. We offer the basic safety objective, which guarantees that the agent in any run will not run out of energy. And then we have the positive reachability objective, which guarantees safety and also ensures that you reach the target state with a probability greater than 0. Then we have the almost sure reachability or reachability, where it's partial reachability, but the probability is equal to 1. And then we have the bouquet objective, where we ensure that the agent visits the set of targets or accepting states infinitely often with the probability of 1. To specify the target states, we have to create a set of target states. In this case, we are only specifying one target state, and that's here. And that's shown as that is shown as the green node here. So once you have the object you want to solve for, we have solvers, which essentially takes the objective, the targets, and the consumption Markov addition process, and use the algorithm proposed in the previous work to calculate the strategy. So each solver gives you the minimum amount of load, the minimum of energy you need for the particular objective in each of the states. It also gives you the strategy, which is obtained by the function getSelector. The two important strategies which we offer are the basic ES, which implements the basic qualitative strategy synthesis algorithms discussed in our previous work. And then we also have some heuristics. The heuristics focus on improving some realistic parameters that are of interest in a real-world problem, which also includes the expected reachability time, which is essentially the expected time it takes to reach any of the targets. You can also add your own solvers. We provide a template to add any solver. And since the code is modular, you can pretty much change just the solver and everything else will work exactly as intended. So this example shows the syntax for creating a solver. So we have energy solvers here, and we show the MDP. So we first obtain the minimum levels of energy needed in each state, and those values are shown here. If you're here, the consumption is 0, and there's only one action, which is deterministic. So you don't really need any energy. So the minimum amount of energy needed is 0. But if you're here, you need at least energy of 1 to be able to reach the target set. And in this case, we actually synthesize a strategy using the bouquet objective. And for the state S, it shows that this is using the qualitative controller synthesis algorithm, and it shows that for any resource greater than 1, essentially for every resource value, you take the action beta. But if you use the heuristic, it shows that for action 1, use beta because that's the only option, but more than 2, use alpha because that's a faster route to the target. This is another example, a larger example where we compute every objective and the scores are shown in every node. I'm going to skip this right now because of the lack of time. So in terms of specifying the mission requirements, given an LTR formula over a set of atomic propositions and a consumption Markov addition process where each state is labeled by a subset of these atomic propositions, we decide if there's a strategy exists that satisfies this LTR formula with the probability 1, and if so, we give a strategy. So we support LTR formula that can be expressed by deterministic Beek automata, and use a spot for translating any LTR formula to a deterministic Beek automata. Here's an example which shows how it works. So we essentially have a simple MDP where we have the initial state, and we try to reach both of the states infinitely often. But if we do it the regular way, where we give this as an accepting state, we only end up actually covering only one of them, which is not the intended behavior. We can express it as this LTR formula, and using that, we first translate it into a deterministic Beek automata using spot, and then we create a product MDP using a product MDP consumption Markov addition process, which uses a labeled consumption Markov addition process with the deterministic Beek automata, and then we solve for a solution for each of the. We obtain a valid initial minimum energy value for each of the state, and also valid strategy. And we also offer integration with Storm, and that enables us to translate models from Prism and Johnny models directly into FiMDP. The two ways of integration, we translate a CMDP to Storm essentially by encoding the energy constraints in states and actions. And Another way is creating a special class of MDP with no cost consumption, with cost labeling the consumption and labels as the reload states. We also include direct support for Prism models and with the convenient interface for parametric models. We skipped this one because of the lack of space, but you can find further details in this particular tutorial. Next, we come to FiMDP environments. It's an open source Python package with environments that model real-world consumption mark-prediction process. The two main examples are UUV Environment, which essentially models unmanned underwater vehicles operating with limited onboard energy in stochastic currents. This is a high-level dynamics model. And we have the AAV environment, which essentially models an autonomous electric vehicle operating in the streets of New York with stochastic energy consumption. Both of these environments are designed to store the utility and scalability of FiMDP, and they also serve as template for users to develop their own environments. Here's an example of UUV environment where we essentially create, the first step is to create the environment, which you do in this particular step. So we essentially give a grid size, a capacity, where the reload states are, and where the target state is. So the reload states are orange, the target state is green, and blue is the initial state. So this particular animation shows how it behaves per particular energy level. So with the sufficient energy level, the agent directly goes to the target and then goes to reload states and loops back to the target to satisfy the Beek objective. But if I change the energy level, the capacity to, let's say, a smaller value, let's say if I change it to 40, then the agent cannot directly go to the target. It tries to go to the target, then realizes that it doesn't have enough energy to go to the target and then go to reload state. So it first goes to reload state, then reloads, and then heads to the target, and then continues the cycle. Next, we have a quick demonstration of the AAV environment. We essentially define a bunch of reload states. So the AAV environment models an autonomous electric vehicle with realistic data in the streets of New York. The green state is the starting state. The red states are target states, and the blue locations are some of the level 3 charging locations in the city of New York. So we specify the reload states and the target states, and then we create the environment. It's a rendering of the environment. After that, we create a strategy. And this, sorry. So I just did not include the minimum amount of energy required to get a valid solution. All right.
Please note that you should wrap up.
Yeah, sorry. So yeah, this provides an animation of one of the runs, and note that every run doesn't have to be the same. So finally, we evaluate a model. We essentially translate the conception MDP into an MDP in Storm, where we explicitly model the resource level in states. And we use Storm model checker because it's supposed to be efficient in terms of time and memory. And we compare it with our approach we use the UUV environment with different grid sizes and capacities. And here are some of the plots. So the FiMDP, as expected, performs better in almost every case except for very small values, where Storm outperforms FiMDP because of its efficient C++ implementation. Note that we are not comparing Storm directly with FiMDP. We're just trying to compare our approach with an approach which explicitly encodes a resource level in the states. It's just that we use Storm because it's supposed to be the most efficient tool. So yeah, conclusions. So we introduced FiMDP, a tool for strategy synthesis and consumption mark-prediction process. and it supports a deterministic wiki LTL objectives. We provide a robust framework for modeling, synthesis, simulation, and analysis of discrete resource constrained stochastic systems, most of which are of practical interest. There's low barrier of entry for the tool. Getting started with the tool is as easy as clicking on the binder link in our GitHub repo. You don't have to install anything. You can just start it with the link, and you can run everything in the web. There are multiple individuals working on active extensions to accommodate other interesting models with stochastic dynamics. And we're also enhancing the FiMDP environment. We are extending the autonomous electric vehicle environment to support multiple different major cities with realistic transit time and energy consumption data. Thank you so much for listening to the talk. I know I had to rush a bit because of the code, but feel free to ask if you have any questions, and you can always email us if you have more questions. Thank you so much.
Okay, thanks for your interesting presentation. Nice tool. So we have time for just one question if someone wants to raise his hand, or I don't see any hands raised here. Okay, so I just have one small question then.
Sure.
So did I understand well that you compared with Storm only on one specific case study? Is that correct?
Yes. We use only one particular environment, and I don't think using a different environment particularly matters. We're just trying to show how it changes with the size of the problem, and how our approach of modeling the problem compares with explicitly modeling the resource level in the state space.
Okay, so you're not planning a larger evaluation comparison, let's say.
Not right now, but we could always increase the size of the UUV environment because it's dynamic. So we can increase the grid size, and we can have a larger problem, and we can evaluate that. Yeah.
Okay. So you're focusing now on adding more functionality, if I understood.
Yes. So I can't speak for other students because I didn't discuss this with beforehand, but they're trying to work on supporting more fundamental models than just Markov, just MDPs. It could be in terms of different levels of observability in terms of in the MDP.
I understand. Okay, so thank you once again
thank you so much
for your nice presentation. And